Oh, it's yourself again. Hi, welcome back. Today we're going to have a look at a second video on uncertainties in higher physics, and we're going to be looking at random uncertainty and systematic errors. By the end of this lesson, you should be able to recognise when a random uncertainty has occurred, be able to calculate a random uncertainty, and be able to recognise when a systematic error has occurred. We're going to start by having a look at random uncertainties. So what is a random uncertainty? A random uncertainty occurs when repeat measurements are taken in an experiment. However, they only apply when the measurements that are taken are different from each other. As in, you repeat an experiment or repeat a measurement and you don't get the same result each time. To calculate a random uncertainty, we use this equation here. Delta x equals the max value minus the minimum value divided by the number of values. Don't be too concerned about delta x. The Greek letter delta is often used to indicate an uncertainty or a change in some value x in this case. So if we took multiple measurements in an experiment, maybe for a time or a distance or a weight, we would take the highest value, the max value, subtract the minimum value or the smallest value, and divide by the number of repeats that we took of that experiment. I have a wee example just to highlight how this would work in practice. A group of students estimate another student's height, a really basic experiment. The following estimates are recorded, and you see that we have 6 estimates of height, and they're all different. If they're all different, this would indicate that there will be random uncertainty in the height. Calculate the mean height and the random uncertainty in the height. So the mean height just means the average height, and you should know how to do that by now. To calculate the mean height, we need to add all the heights together and then divide by the number of heights that we took. Represented as an equation, the mean is the sum of the heights, and that's what that funny wee Greek letter there represents, divided by the number of estimates. So we add all the heights together and divide by 6 because we took 6 estimates of the height, and that gives us a mean average of 1.64 metres. As mentioned earlier, because all the heights are different, this means we have a random uncertainty. If all the estimates were the same, the random uncertainty would be 0. To calculate the random uncertainty, we take our maximum value, subtract our minimum value, and divide by the number of values we took. You can see that the maximum value is 1.70 metres, and the minimum value is 1.59 metres. So we subtract the 1.59 from the 1.7, and divide by our 6 estimates. That will give us plus or minus 0.018 metres, but it's generally good practice to round to the same number of decimal places as the height that we've been measuring. So rounding, we get plus or minus 0.02 metres. We would like to display that as an absolute uncertainty. And so we've got 1.64, that was our mean, plus or minus the 0.02 metres. If you're unsure what I mean by an absolute uncertainty, you need to go back and watch the previous video. We could of course calculate that as a percentage uncertainty. Again, if you don't know how to do that, go back and see the previous video, but we're looking for 0.02 as a percentage of 1.64. Try and work it out if you want, but it's plus or minus 1.2%. In the second example, a toy car is released down a slope and the time to reach the bottom is recorded. The experiment is repeated 5 times. The following times were recorded: 1.83 seconds, 1.64, 1.78, 1.78 again, and 1.87. Calculate the mean time and the random uncertainty. Again, we have different results. This would mean that we have a random uncertainty. Just because we have two results that are the same does not mean to say that the random uncertainty is 0. I'll give you a minute to pause the video and have a go. Okay, so to calculate the mean time, again, we add all those times together and we divide by 5 because we recorded 5 times. So we get T bar. T bar, the T with the little line, the little bar on the top. The bar is often used in maths to indicate an average or a mean, and so we add all those times together, divide by 5 because we have 5 times, and we get 1.78 seconds. To calculate the random uncertainty, again, pause the video, have a go. Alright, so we need to take our maximum value, which is 1.87, subtract our minimum value, 1.64, divide by 5 because we have 5 times, and that gives us plus or minus 0.05 seconds because we have rounded to the same number of decimal places as the times. Again, displaying this as an absolute uncertainty, we've got 1.78 plus or minus 0.05 seconds. The third example that I want to go over with you is directly from the 2016 exam paper. The link is on the screen if you want to go to the SQA website and download that paper and have a look at it yourself. We're only going to do part of the question, not the whole question. We've got a lot of bump there, a toy car being released down a ramp. The student's going to use the toy car to investigate the force of friction between its wheels and a carpet. Okay. It says that the student repeats the procedure several times and records the following measurements and uncertainties. I know they've measured the mass of the car, the height of the ramp, and there are uncertainties there too, but we're not concerned about them. We're only concerned about the distance. You can see there's 5 stopping distances there. 1.31, 1.40, 1.38, 1.41 and 1.35. And the first question asks us to calculate the mean distance D travelled by the car. I'm going to give you a minute to pause the video and have a go. Alright, so to calculate the mean distance, or D bar, we add all those distances together and divide by 5 because we have taken 5 measurements of distance, and we get 1.37 metres. The next question though asks us to calculate the approximate random uncertainty in this value. Again, I'm going to allow you to pause the video and have a go. Are you done? Okay. So, delta D, or the uncertainty in D, is equal to the maximum value, and you can see our largest value is 1.41, minus our minimum value, 1.31, divided by 5, because we've taken 5 readings, and that gives us plus or minus 0.02 metres. So some final points about random uncertainties. Repeating measurements reduces the random uncertainty. You get that from the equation where you're dividing by the number of repeats, the number of measurements you took. The bigger the number you divide by, the smaller your random uncertainty. This is the reason why experiments are repeated. Maybe in the past you've heard a science teacher asking you to repeat an experiment. And maybe they've told you that the experimental results are more reliable by repeating the experiment. In reality, repeating the experiment reduces the random uncertainty. It makes us more confident in our measurement, and it makes the measurement or experiment more reliable. However, that's not in every case. Many times if we're measuring something like a voltage, we will get exactly the same voltage every time we measure it. If this is the case, there's no point in repeating the experiment again and again and again. Because when we repeat the experiment, our random uncertainty is going to be 0. There is no point in repeating the experiment because we can't reduce the random uncertainty any further. So random uncertainties are only useful, and repeating experiments again and again and again is only useful if we are getting different measurements every time that we do it. So what about systematic errors? What are they? A systematic error is a fundamental flaw or bias in the equipment or the experimental procedure. It means that every time you conduct a measurement or experiment, it affects every single measurement taken. Random uncertainties can be reduced by repeating measurements or readings. Systematic errors can't. Every time you conduct an experiment again or repeat an experiment, the same systematic error will creep in and will mess up your results every time that you do it. Systematic errors can only be overcome by ironing out the flaw or the bias, changing the experiment in the first place. The problem with systematic errors is that usually they're only really known after collecting and analysing the data, a lot of the time from graphing the data. A very famous case of a systematic error creeping in was when NASA built the Hubble Space Telescope in the 90s. The Hubble Space Telescope is a reflecting telescope. It used a massive mirror to collect light, and the mirror has an ever so slight curve to it. The problem with the mirror and the curve was they ground the mirror to a perfect curve, but it was the wrong curve. So when they sent the space telescope up into space, the software they were using was analysing the wrong data because it was expecting data from a certain curvature of mirror, but in reality they had ground it to a different curvature. On the image on the left is an image of a galaxy before they were able to correct the curvature, and on the right is the image where they managed to correct the curvature. They only managed to correct the experiment by physically sending astronauts into space to apply and connect extra equipment onto the Hubble Space Telescope. You're more likely to see a systematic error creep in when you're dealing with graphs, for example, when you're analysing the data, and normally through graphing. Maybe you've been doing an experiment of measuring a voltage or a current through a resistor, and you're fully expecting a straight line through the origin. You're fully expecting a directly proportional graph. However, let's say you get your results, you plot your graph, and you get something like this. And instead of the graph intercepting at the origin, you get it intercepting at +1 volt. Nightmare. This would indicate that there is a voltage present in your circuit that shouldn't be there. Maybe it's from a capacitor that you haven't discharged or something like that. This means that every voltage measurement you took has +1 volt added onto it. So you need to take steps to either correct your data or go back and correct your circuit or the way that you're measuring the voltage in your circuit. So, a random uncertainty has occurred when we have multiple readings and they are different. You should be able to calculate a random uncertainty because we had a look at the equation, the maximum value minus the minimum value divided by the number of values, and we went over a couple of examples. So go back and have a look at that if you're still a little unsure. And we should recognise that a systematic error has occurred normally when we're analysing data through graphing, and a perfect example is when we're expecting a straight line through the origin, but we don't get that. Anyway, I'm off. Many thanks for watching. Please like and subscribe, and I'll catch you for the next video where we'll look at combining uncertainties. So what happens when we have a reading uncertainty and a random uncertainty? Cheerio.